Meet the four solids. These triangle meshes are the characters in R. Neville's morph of the Minkowski sum. They work together to generate a smooth animation that can best be described as an explosion of geometric shapes. Successfully completing this project demanded efficient memory usage for many computations needed at each frame. Please notice that the control solids are completely customizable. We've built in a lot of cool functionality that gives the user close to full control over the look of his or her solid. What you're looking at is the Minkowski sum of four solids mapped over time using a Neville's interpolation. Now, what exactly is a Minkowski sum? The Minkowski sum combines the shape characteristics of its arguments. In simple terms, the Minkowski sum grows a solid by another solid. What's interesting about this Neville's interpolation is that at any point in time, the morphing solid is being affected by all four control solids. As you watch the animation, you should appreciate the complexity of the morphing shape. I know that during our development process, the sheer quantity of calculations needed to draw the shape overwhelmed our computers a couple times. So it's safe to say that we're proud of the visual that you see in front of you. The entire animation can be broken down into two simple morphs. A triangle face morphs into a single point. The linear interpolation between the endpoints of two edges generates a moving quad. After the mapping is complete between solids, these two visuals are repeated over and over to generate the final Neville animation. You're looking at an early version of the animation during our development process. The green figures that you see moving represent the faces of the first solid mapped to the vertexes of the second solid. Here are the vertexes of solid A mapped to the faces of solid B. Finally, we have the edge-to-edge animation. The blue moving figure is made up of a bunch of traveling quads. Here you can see a graphical representation of Neville's algorithm. As you can see, it is a recursive algorithm, and you can consider P0 through P3 to be the four control solids, and the arrows to represent linear interpolations. Now, we went ahead and implemented a Bezier interpolation of a Minkowski morph, and there are a couple of differences from the Neville version. As you can see, the Bezier version, the morph stays within the convex hull of the control solids. Georgia Tech's very own Professor Rossignac wrote a paper about Bezier metamorphosis back in the early 90s, and in this paper, one of the things that he did was to replace vector addition with Minkowski addition. We translated that thought over to our Neville's interpolation. And that about wraps it up for this video. We hope you enjoyed it, and thanks for tuning in.